The sun does not invite you. It does not beckon. It radiates a warning so ancient and so absolute that every civilization in human history encoded the same lesson into myth, religion, and fear. Do not approach. Do not reach. Do not touch. And then we did. A spacecraft no larger than a family car crossed a threshold that no object built by human hands had ever crossed before. It pierced the outer atmosphere of a living star, not flew past it, not orbited it from a safe distance. It entered it. It submerged into the plasma, the fire, the electromagnetic violence that makes our sun a God-class engine of destruction. And it came back. What it brought with it shattered assumptions that physicists had held for over a century. The sun is 93 million miles away. That number sounds like safety. That number sounds like distance. But distance in space is not protection. The sun's influence doesn't end at its visible surface. It doesn't stop at the golden corona visible during an eclipse. The sun's atmosphere, its outer shell of charged plasma and magnetic chaos, extends so far into space that we are already inside it. Right now, as you exist in this moment, breathing, thinking, living, you are inside the sun. You are standing in the outermost layer of a stellar atmosphere that reaches beyond Mars, beyond Jupiter's moons, touching the very edge of the solar system itself. The boundary between the sun and empty space does not exist where you think it does. Parker's solar probe crossed what scientists call the Alphen critical surface, the point where the sun's gravity and magnetic field become so dominant that the solar wind, the river of charged particles bleeding from the star, can no longer escape back into the corona. It is the point of no return. The photons that carry light can leave. But the plasma, the raw, ionized matter of the sun itself, cannot flow back. Parker crossed into the region where the sun's material is still gravitationally bound to the star. Parker crossed into the sun. The temperature at that boundary is not measured in hundreds of degrees. It is not measured in thousands. The outer corona, the place a spacecraft just visited, burns at over 2 million degrees Celsius. The surface beneath it, the photosphere you see when you shield your eyes and look up on a clear afternoon, is only 6,000 degrees. The corona is 300 times hotter than the surface of the star itself. This is physically impossible, and it is happening. Every model of thermodynamics built since the 19th century says that heat flows from hot to cold. From the core outward, temperatures should fall. The interior of the sun reaches 15 million degrees. That is where nuclear fusion forges helium from hydrogen and releases the light that powers all life on this planet. Moving outward, the photosphere drops to 6,000 degrees. Logical, expected. Then something happens. Something unnamed. Something that still does not have a complete explanation. And the temperature explodes back upward to 2 million degrees and beyond. The heat is going the wrong direction. Parker flew through that impossibility. Its instruments recorded it not as a theoretical anomaly in an equation, but as a physical reality pressing against its heat shield at over 1,400 degrees Celsius. The shield, a carbon composite structure 12 centimeters thick, stood between the most advanced scientific instruments humanity has ever launched and the raw plasma of a stellar atmosphere. On one side of that shield, science. On the other side, the sun. What came back in the data was not reassurance. It was not a clean set of numbers that confirmed what we already believed. What came back were structures, behaviors, patterns inside the solar wind that no simulation had predicted and no theory had prepared us for. phenomena that moved faster than they should, magnetic fields that folded back on themselves in configurations that looked almost organized. The scientists who reviewed the first data transmissions described their reaction in the language of science. Careful, measured, methodical. But read between the lines of their published papers, and you find the same word appearing again and again. Unexpected. That word in astrophysics is not neutral. It is not routine. When something is unexpected at this scale, it means the model is wrong. And when the model is wrong about the nearest star, the star that created every atom in your body, that holds every planet in this system in gravitational bondage, that will one day expand and consume the orbit of the Earth itself. The implications do not stay in the laboratory. They expand outward, like light, like heat, in every direction at once. We touch the sun, and what we found there suggests that everything we thought we understood about the engine at the center of our solar system, about energy, about heat, about the invisible architecture of magnetic fields that thread through space like the nervous system of a living thing, was only the surface. And the surface, it turns out, was never where the answers lived. Before there was Earth, before there was ocean, before the first carbon atom bonded with the first hydrogen atom in the first organic molecule that would eventually, billions of years later, produce something capable of asking questions about its own existence. There was the sun, not as a finished object, not as the stable golden sphere that rises every morning with the mechanical reliability of a clock. The sun began as a wound in space, a region of cold molecular gas and dust so vast it dwarfed the entire distance between our solar system and the nearest star. And then something disturbed it. A shock wave from a dying star nearby. A supernova whose name we will never know, whose light burned out before any eye existed to witness it. Compressed that cloud. Gravity did the rest. The cloud collapsed inward. It spun. It heated. At the center, where the pressure became incomprehensible, where matter had nowhere left to go, the temperature crossed 10 million degrees and a new process ignited. Hydrogen began fusing into helium. That ignition happened 4.5 billion years ago. It has not stopped for a single second since. Right now, every second, the sun converts 600 million tons of hydrogen into helium. Every second, the mass that disappears in that process, the small fraction that does not become helium, but instead transforms entirely into energy, amounts to 4 million tons of matter converted into pure radiation every single second. That energy travels outward through the body of the sun, bouncing, scattering, absorbed, and re-emitted by particles of plasma over and over again, in a process so slow that a single photon of light, born in the nuclear core of the sun, takes between 100,000 and 1 million years to fight its way to the surface. 1 million years of traveling through the body of a star, and then 8 minutes to reach your eyes. The light entering your retina right now is older than modern humanity. It was born before Homo sapiens walked the African savanna. It was already traveling through solar plasma when our ancestors were still learning to chip stone into tools. And yet, it arrives in your eye in the same instant as the light born a millisecond ago beside it. The sun is not just a source of light. It is a library of time. Every photon carries within its energy the record of the conditions that existed in the core when it was born. The density, the temperature, the exact configuration of protons that collided to create it. We cannot read that library directly. The photons lose their history as they scatter. But Parker's solar probe did not go to read old light. It went to read something much stranger. The solar wind is not wind in any sense that language was designed to describe. It is not a movement of air. There is no air. It is a continuous, supersonic outflow of ionized plasma. Electrons stripped from their atoms, protons traveling freely, magnetic fields woven through everything like invisible thread. Erupting from the sun's corona and expanding outward in all directions simultaneously at speeds between 300 and 800 kilometers per second. Every second, the sun loses over 1 million tons of its own material into this wind. Every second, the star bleeds into space. That bleeding created this solar system as we know it. It sculpted the orbits of the planets by pushing and pulling on their magnetic fields. It stripped Mars of its atmosphere over billions of years, slowly erasing whatever chance that world had of becoming something other than a cold, red desert. It is the reason the Earth's magnetic field matters, not as an abstract shield against cosmic radiation, but as the specific, essential barrier that kept our atmosphere from being dissolved by the same stellar wind that murdered Mars. Without the magnetic field generated by the churning iron core beneath your feet, the solar wind would be stripping away the air above you right now. Not over millions of years, over thousands. The Earth survives because of a magnetic accident, a geological lottery. The fact that our core is still liquid, still convecting, still generating the dynamo that wraps our planet in invisible protective fields, that is not guaranteed. That is not permanent. Mars once had a magnetic field too, and it died. Parker flew into the source of all of this, into the place where the solar wind is still forming, still accelerating, still becoming the force that shapes planetary fates. And the first thing it found was that the solar wind does not accelerate the way physics said it should. For decades, the standard model of solar wind acceleration described a smooth, continuous process. The plasma leaves the corona, gravity pulls it back. But the thermal pressure and magnetic forces overcome gravity, and the wind gradually builds speed as it moves outward, like water flowing down a gradual slope. Clean, predictable, solvable with differential equations that any graduate student in astrophysics could work through on a chalkboard. Parker found something else entirely. Inside the corona, embedded in the solar wind like hidden architecture, Parker detected structures that physicists have named switchbacks. The magnetic field of the solar wind does not flow outward in a single, organized direction. It folds, it kinks, it reverses on itself in sharp, sudden turns. The field line pointing toward the sun, then abruptly flipping to point away, then folding back again. Like a river that periodically flows upstream for miles before resuming its journey to the sea. These reversals happen in seconds. The plasma associated with these switchbacks moves faster than the surrounding wind, significantly faster. And at the moment of each reversal, the instruments detected sharp bursts of energy, a kind of invisible percussion, a crack of electromagnetic force with no equivalent in any model. Where do they come from? The honest answer is that no one fully knows. The leading hypotheses involve processes at the solar surface, magnetic reconnection events at the base of the corona, where oppositely oriented field lines snap together and release energy, or velocity shears in the plasma where fast and slow streams collide and generate turbulent structures that propagate outward. But the frequency, the scale, the energy content of what Parker recorded far exceeds what the theoretical models predicted. The switchbacks are everywhere. They are not rare anomalies. They appear to be fundamental features of the young solar wind, and possibly fundamental to the mechanism that heats the corona to its impossible temperatures. This is the part that deserves to be said slowly, because the mind resists it. The corona is hotter than the surface. The atmosphere of the sun is hotter than the sun itself. And the leading explanation for this impossible heat, the mechanism by which the corona maintains temperatures 300 times higher than the photosphere directly below it, appears to involve these magnetic switchbacks, these kinks and reversals and reconnection events. The sun may be heating its own atmosphere from the outside in through a process of continuous magnetic violence, a kind of perpetual electromagnetic storm running just above the visible surface, invisible to any telescope that can only capture light. Parker did not observe this from a distance. Parker flew through it. Think about what that means in human terms. Imagine building a vessel that could descend into the eye of a hurricane, not to observe the storm from above, but to pass through the wall itself, through the rotating bands of maximum wind and pressure, into the calm eye, and then out the other side, recording every measurement with instruments sensitive enough to detect changes in magnetic field strength across distances of kilometers. Now replace the hurricane with a phenomenon 3 million times larger, operating at temperatures that would vaporize any material humanity has ever worked with, threaded through with magnetic fields powerful enough to accelerate particles to near relativistic speeds. That is what Parker did, and it did it while remaining in continuous communication with Earth, transmitting data at a distance where signals take 8 minutes to arrive. Guided by engineers who could not intervene in real time, who had designed every autonomous system years in advance and then surrendered control to the spacecraft entirely. There is a philosophical weight to that surrender that goes beyond engineering. The moment Parker crossed the Alphen surface, the moment it entered the gravitationally bound atmosphere of the sun, it was beyond all reach. The decisions it made to protect itself, to orient its heat shield, to prioritize its instruments, were decisions encoded by human minds into software and then released. The humans who built it could only wait. They could only trust the machine they had made, the way a sculptor must eventually stop adding to the clay and accept the form that exists. And the form that came back, the data, the measurements, the records of a spacecraft inside a living star, revealed that the sun is not a simple object with a simple boundary and a simple atmosphere. It is layered. It is dynamic. It is threaded through with structures and processes that operate on scales ranging from kilometers to hundreds of millions of kilometers simultaneously. The solar wind is not uniform. The corona is not static. The magnetic field is not a passive background. It is an active, energetic, constantly reorganizing architecture that drives phenomena from the smallest turbulent eddies in the plasma to the largest explosive eruptions that dwarf the entire diameter of the Earth by factors of hundreds. And underneath all of this complexity, underneath the switchbacks and the reconnection events and the anomalous heating and the supersonic plasma rivers, there is a question so fundamental that it has been sitting unanswered at the center of solar physics for 80 years. Why does the corona exist at all? Not in the sense of how it formed in the early solar system, but in the thermodynamic sense, in the sense that the laws of physics, as we understand them, provide no satisfying mechanism for a body to be cooler at its surface than in its atmosphere. The photosphere radiates. The photosphere loses energy. The corona should cool as it moves away from the energy source below it. Instead, it heats. The energy flows in the wrong direction. Parker's data has not solved this mystery. It has deepened it, because now we know that the mechanisms at work inside the corona are more complex, more layered, more energetic than any model assumed, which means that whatever process is responsible for the impossible heat, whatever is driving energy upward into the corona rather than allowing it to dissipate outward, is a process operating at a scale and through a mechanism that our current physics has not yet named. We are looking at a phenomenon that is real, that is measurable, that affects every planet in this solar system, that has been heating the corona every second for 4.5 billion years, and we do not know what it is. That is not a failure of science. It is the nature of science. Every answered question reveals the outline of 10 unanswered ones behind it. But there is something humbling, something genuinely vertiginous about standing at this particular threshold and looking through it. Because the sun is not exotic. The sun is not distant. The sun is the star we named first, the star we worshipped first, the star we thought we understood. And it is telling us through the instruments of a spacecraft smaller than a car that understanding is not yet complete. It may never be complete. The universe does not owe us legibility. It does not organize itself around the comfort of human comprehension. The laws of physics are not written for minds like ours. They were discovered by minds like ours, slowly, imperfectly, through centuries of accumulated error and correction. What Parker is revealing is that the nearest star, the most studied object in the sky, the engine of all biological life on this planet, is still capable of surprise. And surprise at this scale carries consequences. There is a sound the sun makes that no human ear will ever hear. Not because it is too faint, not because it is too distant, but because it travels through a medium that cannot carry vibration the way air does. Through plasma, through magnetic fields, through the near vacuum of interplanetary space where pressure waves have no molecules to move between. The sun's acoustic oscillations, the deep structural vibrations of its interior, the way its body rings like a bell struck by the hammer of its own nuclear processes. These can only be detected by instruments measuring the subtle Doppler shifts in the light leaving its surface. The sun is singing. It has been singing for 4.5 billion years, and we learned to hear it only in the last few decades. What Parker added to that listening was not sound. It was texture. The data Parker returned from inside the corona is not a single clean signal. It is a symphony of overlapping phenomena, each operating on its own frequency, its own time scale, its own spatial scale, and all of them interacting with everything around them simultaneously. To process this data is not like reading a weather report. It is like being handed a recording of every instrument in an orchestra, playing simultaneously with no score, no conductor's notes, no separation between tracks, and being asked to reconstruct not just the music, but the physical architecture of the concert hall, from the reverberations alone. And yet the instruments aboard Parker were designed precisely for this. Designed to separate signal from noise at the boundary of a star. The Field's instrument suite measured electric and magnetic fields with a sensitivity that could detect variations smaller than the width of a human hair across distances of hundreds of kilometers. The sweep instruments, the solar wind electrons, alphas, and protons investigation, counted individual particles, not populations, not averages. Individual ions and electrons passing through detectors the size of a dinner plate, traveling at hundreds of kilometers per second with enough precision to measure their velocities, their temperatures, their densities, their compositions. The WISP-R cameras image the corona and the solar wind structures within it using visible light, capturing for the first time the internal texture of the young solar wind from inside. these instruments did not just collect data. They collected a new language, and one of the first things that language communicated was the existence of structures inside the solar wind so coherent, so organized, so persistent across space and time that calling them turbulence feels inadequate. Turbulence implies chaos. What Parker found had geometry, plasma jets, narrow, high-speed streams of material erupting from the lower corona and threading into the solar wind above, carrying energy and momentum in concentrated channels rather than diffusing it uniformly into the surrounding plasma. These jets had boundaries. They had internal structure. They moved through the surrounding solar wind the way a river moves through a lake, maintaining their coherence, their identity, their direction, against the pressure of everything around them. The physical analogy that forces itself upon the mind is uncomfortable in its implications. Rivers do not form an open ocean without a source and a channel. They require topography. They require gradients. They require the invisible hand of some organizing principle that concentrates flow rather than dispersing it. In the solar wind, that organizing principle is the magnetic field. And the magnetic field, it turns out, is far more structured at the base of the corona than any remote observation had suggested. Parker found that the magnetic field near the sun is not a smooth, gradually weakening force that simply stretches outward into space as the solar wind carries it away. It is knotted. It is braided. It contains regions of intense concentration, separated by regions of relative calm. Like the fibrous structure of a muscle, bundles of field lines wound together, carrying enormous energy density, then releasing that energy through reconnection events that pulse outward through the corona like shock waves through water. Every one of those reconnection events, every snap of magnetic field lines, is an explosion, not a metaphorical explosion, a physical release of energy stored in the magnetic topology of the corona, converted suddenly into kinetic energy, thermal energy, particle acceleration. The smallest of these events are called nanoflares. The name was coined theoretically by the physicist Eugene Parker, the man after whom the spacecraft is named, who proposed in 1988 that the corona might be heated not by a single large mechanism, but by an uncountable number of tiny explosive events, each individually below the threshold of detection, but collectively contributing enough energy to maintain the corona's impossible temperature. Parker the spacecraft found evidence that Parker the physicist was right. Not definitive proof. Science does not work in the currency of definitives. But the measurements inside the corona revealed a background of energy deposition consistent with the nanoflare model. A constant, distributed heating that is neither smooth nor uniform, but statistical. Probabilistic. The corona is not heated by a furnace with a thermostat. It is heated by a storm of invisible explosions, each one brief and small, collectively amounting to a thermal output so enormous that it maintains millions of degrees across a region larger than 100 Earths stacked in a line. Consider what that means for the scale of what we are talking about. A nanoflare releases approximately 10 to the power of 17 joules of energy. That is 100 quadrillion joules. A nuclear weapon of the largest class ever detonated by humanity released approximately 2.4 times 10 to the power of 17 joules. A single nanoflare releases roughly the same energy as the most powerful thermonuclear bomb ever built. And these events are happening continuously across the entire surface of the sun at a rate of billions per second. Billions of nuclear weapon-scale explosions per second. Continuously. For 4.5 billion years. And this is the mechanism that heats the atmosphere. Not the nuclear fusion in the core, not the radiative pressure from the photosphere. The corona is sustained by what amounts to an endless, perpetual, self-organizing artillery barrage of magnetic energy releases happening just above the visible surface of the star. Invisible to optical telescopes, detectable only by their thermal signature and their contribution to the solar wind's energy budget. The sun is not burning. The sun is detonating. Continuously, in every direction, at every scale simultaneously. This realization carries a weight that extends beyond solar physics. Because the sun is not unique. Every star in the observable universe, every one of the estimated 200 billion trillion stars that burn within the visible horizon of our telescopes, is, in principle, doing some version of this. Every stellar corona in the universe may be maintained by some variant of this magnetic violence. Every solar wind pouring from every star, shaping every planetary system, eroding or protecting every atmosphere around every world that orbits them, is driven by the same fundamental physics. The magnetic reconnection events happening above the sun right now are happening above the stars in Orion, above the red dwarfs that outnumber all other stellar types combined, above the blue giants burning so fast they will exhaust their fuel in millions rather than billions of years. The universe is full of stars detonating their own coronas into space. And on the planets orbiting those stars, if there are planets, and if those planets have magnetic fields, and if those magnetic fields are strong enough, and if those worlds had billions of years of stability to allow chemistry to organize itself into biology, then perhaps some of those worlds have something looking up at their own sky, something asking its own questions about the light that falls on it and what it means and where it comes from. Parker brought us to the threshold of that question in a way that no mission had before. Not by finding life, not by detecting another civilization, but by revealing the mechanism that all stellar systems share. The universal grammar of stars, the process by which a nuclear furnace wraps itself in a corona and bleeds that corona into space and sculpts everything around it through invisible magnetic force. This is the context in which the Parker Solar Probe mission must be understood. It was not a mission to one star. It was a mission to understand what stars are. And what stars are is something that shapes the fate of worlds. The solar wind carries more than energy. It carries history. Every particle in the solar wind began its journey in the nuclear core of the sun, fused from hydrogen that entered the solar system with the original molecular cloud 4.5 billion years ago. Some of that hydrogen, a small but real fraction, came from the supernova that seeded the cloud before the sun formed. The solar wind carries atoms that were forged inside a star that died before our sun was born. Those atoms left the sun's corona and traveled outward, and some of them struck the dust grains in the outer solar system and are now preserved in comets and asteroids. Some of them struck the early Earth and became part of the atmosphere. Some of them became part of the chemistry that eventually organized itself into the first self-replicating molecules. You are made, in part, of the solar wind of a dead star. Parker measured the composition of the solar wind with enough precision to begin tracing these elemental signatures. To begin asking, which parts of the corona produce which kinds of wind? Are there regions of the sun that preferentially accelerate certain elements? Are there compositional differences between the slow solar wind that emerges from the equatorial regions and the fast solar wind that pours from the polar coronal holes at speeds exceeding 700 kilometers per second? The answer is yes. The solar wind is not homogeneous. It is a complex, structured, compositionally variable river of stellar material. organized by the magnetic topology of its source regions, carrying chemical fingerprints of the specific plasma populations that generated it. Slow wind and fast wind differ not just in speed, but in temperature, density, composition, and magnetic field structure. They interact where they meet, forming co-rotating interaction regions. Invisible walls of compressed plasma that sweep through the solar system like a lighthouse beam, striking anything in their path with elevated particle fluxes and magnetic field enhancements. Those interactions matter. They matter for spacecraft. They matter for astronauts traveling beyond the protective magnetosphere of Earth. And they matter in ways still being understood for the fragile electronics of the satellites that now constitute the nervous system of modern civilization. The sun does not merely warm the Earth. It probes it. It tests it. It pushes against the magnetic shield that stands between the surface and space. And when the sun pushes hard enough, during coronal mass ejections, during solar flares, during the passage of high-speed solar wind streams, that shield compresses and distorts and allows energetic particles to pour into the upper atmosphere, generating the auroras, disrupting radio communications, inducing currents in long-distance power lines. In 1989, a geomagnetic storm caused by a coronal mass ejection collapsed the entire power grid of the Canadian province of Quebec in 90 seconds. 6 million people lost electricity. Transformers were destroyed by induced currents. The storm's energetic particles penetrated to latitudes as low as Texas, producing auroras visible to millions of people who had never seen them before. The total economic damage was in the billions, and the storm that caused it was not exceptional. It was not a once-in-a-civilization event. It was a moderate solar event on the scale of what the sun produces regularly over the course of an 11-year solar cycle. The Carrington event of 1859 was not moderate. It was the most powerful geomagnetic storm in recorded history, a solar flare and coronal mass ejection so intense that the resulting currents set telegraph equipment on fire across North America and Europe. Operators reported receiving electric shocks from their equipment. Some stations continued sending and receiving messages for hours after disconnecting from their power sources entirely, powered solely by the induced current from the storm. The aurora was visible at equatorial latitudes, in Cuba, in Colombia, in Hawaii. If a Carrington-class event struck Earth today, the consequences would not be telegraph operators receiving shocks. They would be the simultaneous failure of the global satellite network, the disruption of GPS navigation systems on which aviation, shipping, and financial transactions all depend, the induction of currents in continental power grids capable of permanently destroying the high-voltage transformers that take years to manufacture and cannot be quickly replaced. The estimated economic impact of a Carrington-class event on modern infrastructure is between $1 and $10 trillion in the first year alone. And the recovery time, the time required to replace destroyed infrastructure and restore normal function, is estimated in years to decades. This is not a theoretical risk. It is a historical fact expressed at a scale our infrastructure had not yet reached in 1859. The sun has done this before. The sun will do this again. The question is not whether. The question is when. Parker's solar probe is, in this light, not merely a scientific mission of curiosity and wonder. It is a reconnaissance mission. It is humanity's attempt to understand the mechanism that drives these events before the next major one arrives. To read the magnetic topology of the corona well enough to predict when a large-scale reconnection event is about to occur. To give the world hours or days of warning rather than the minutes of warning current technology provides. Minutes are not enough. Hours might be. Days would allow the orderly shutdown of vulnerable systems, the rotation of satellites to protective orientations, the preparation of grid operators worldwide. The difference between a manageable disruption and a civilizational catastrophe might be measured in the quality of solar wind data flowing back from a spacecraft the size of a car, orbiting closer to the sun than any instrument has ever orbited before. That is the stakes beneath the science. That is the weight behind the data. Parker is not just teaching us about the sun. Parker is buying us time. And time, as the sun well knows, is the only currency that matters. There is a force threading through the solar system that you cannot see, cannot feel, cannot taste or smell or hear. And yet, it governs the motion of every charged particle between here and the edge of interstellar space. It bends the paths of cosmic rays arriving from distant galaxies. It channels the solar wind into spiral arms that coil outward from the sun like the grooves of a vast, slowly unwinding spring. It connects the surface of the sun to the surface of the Earth through invisible lines of influence that span 150 million kilometers of near vacuum and arrive here still carrying the signature of the magnetic events that generated them 8 minutes earlier. It is the heliospheric magnetic field, and Parker's solar probe flew through its birthplace. To understand what Parker found there, you first need to understand what the heliospheric magnetic field is. Not as an equation, not as a diagram in a textbook, but as a physical reality that permeates the space your planet moves through every second of its orbit. The sun rotates. It completes one rotation approximately every 25 days at its equator, slightly slower at its poles. As it rotates, it continuously emits the solar wind in all directions. But the magnetic field threading through that solar wind is anchored at one end to the sun's surface. And as the sun rotates, it drags the foot of each field line around with it, while the other end stretches outward at solar wind speeds. The result is a spiral, a vast three-dimensional Archimedean spiral of magnetic field lines winding outward from the sun across the entire solar system, like the pattern of water from a spinning garden sprinkler scaled up to the size of a planetary system. At the distance of the Earth, a field line that left the sun points not directly back toward it, but at an angle of approximately 45 degrees. The field line you are immersed in right now connects to a point on the sun's surface that is already a quarter rotation away from where it was when that field line left. This structure, called the Parker spiral, named once again for the same physicist whose theoretical intuitions have shaped solar physics for 60 years, was predicted mathematically before it was ever measured. Eugene Parker predicted the solar wind itself in 1958. In a paper so contrary to the prevailing view of a static solar atmosphere that it was initially rejected by 2 peer reviewers before a third recognized its validity. He predicted the spiral structure of the heliospheric magnetic field from first principles, from the geometry of a rotating magnetized sphere emitting a continuous supersonic outflow. He was right. And for 60 years, every spacecraft that measured the magnetic field of the solar wind confirmed his mathematics. But Parker's solar probe did not go to confirm. It went to the place where the spiral begins, to the corona, where the magnetic field transitions from being dominated by the sun's interior dynamics to being carried outward by the solar wind, to the Alfvén surface, that critical boundary where the solar wind finally overcomes the sun's magnetic tension and begins its journey outward, and below it, into the region where the field is still fully controlled by the sun, where it is still part of the star. And what it found below the Alfvén surface was that the spiral does not begin cleanly. The transition from a sun-dominated magnetic field to a wind-dominated one is not a sharp line. It is a turbulent, dynamic, constantly shifting boundary that moves inward and outward as the corona breathes and erupts and reorganizes. Parker crossed this boundary multiple times on each close approach to the sun, dipping below it, rising above it, dipping below again, like a boat crossing a tidal line that advances and retreats with each wave. Each crossing was a passage between two physical regimes, as distinct as the difference between being inside a river's current and standing on the bank watching it flow past. Inside the Alphen surface, the plasma does not escape. It circulates. It is bound to the sun by magnetic tension, in the way water droplets are held to a spinning wet ball by surface tension, flung outward by centrifugal force, pulled back by adhesion, finding a dynamic equilibrium at the surface that is not a solid boundary, but a statistical balance of competing forces. The magnetic field in this region is not a passive tracer carried by the plasma. It is the dominant actor. It channels the plasma. It confines it. It organizes it into structures that persist long enough to be measured, long enough to be mapped, long enough to reveal the hidden architecture of the corona's interior. That architecture is breathtaking in its complexity. Parker's instruments revealed that the corona is divided into regions of dramatically different character that neighbor each other with sharp boundaries. Regions where the magnetic field is open, where field lines connect the solar surface to interplanetary space and allow plasma to stream freely outward, alternate with regions where the field is closed, where field lines arch back to the surface and trap plasma in loops that glow brilliantly in X-ray wavelengths, visible from Earth through specialized telescopes as the bright, arching structures of active regions. The boundaries between these open and closed regions are not gradual transitions. They are interfaces. And at those interfaces, when the solar wind pushes outward through an open field region and drags the boundary of a closed field region with it, the magnetic topology must change. Field lines must reconnect. Energy must be released. And the plasma trapped in the closed loops must either be released into the solar wind or compressed further into the closed structure. This process, this continuous topological renegotiation at the boundaries between open and closed magnetic regions, is one of the primary engines of solar wind variability. It is why the solar wind that strikes Earth is not a smooth, constant flow, but a gusty, variable river full of structures, discontinuities, and sudden changes in direction and intensity. Every variation in the solar wind that eventually becomes a geomagnetic storm began as a local magnetic topology change in the corona. Every aurora that has ever illuminated a polar sky began as a reconnection event at a coronal boundary. Parker measured these boundaries from the inside. The implications of that measurement extend far beyond solar physics. Because the sun is not the only star with a corona and a stellar wind and a heliosphere. Every star with a convective envelope, every star with a churning outer layer that generates a magnetic dynamo, has some version of what Parker measured, and many of those stars are far more magnetically active than the sun. Red dwarf stars, the most common type of star in the galaxy, are smaller and cooler than the sun, but magnetically ferocious. Their coronas are proportionally more luminous in X-rays. Their stellar winds are more variable. Their flaring activity is more frequent and more intense. A planet orbiting a red dwarf in the habitable zone, in the range of distances where liquid water could theoretically exist on its surface, orbits far closer to its star than the Earth orbits the sun. It is immersed in a stellar wind environment far more hostile than ours. Its magnetosphere, if it has one, is constantly battered by energetic particles and coronal mass ejections at a frequency and intensity that would challenge the survival of any atmosphere. This is one of the central questions in the search for habitable worlds beyond our solar system. Not just whether a planet is the right distance from its star for liquid water, but whether its star is the right kind of star to allow an atmosphere to survive long enough for life to develop. Parker's measurements of the solar corona and solar wind are providing the physical framework for answering this question across the galaxy. Because understanding how our sun's magnetic activity shapes our planetary environment is the first step toward predicting how any star's magnetic activity shapes any planetary environment. We are not just studying the sun, we are developing the vocabulary to assess the habitability of worlds we have never visited. Around stars we can barely resolve as points of light, using physics we are still learning to read. But there is another dimension to what Parker found inside the corona that reaches beyond planetary habitability and into something more fundamental. Something that touches the nature of plasma itself, of the fourth state of matter that makes up 99% of the visible universe. Plasma is not a gas. This distinction matters more than it might seem. A gas is a collection of electrically neutral particles interacting primarily through collisions, atoms and molecules bouncing off each other, transferring energy through direct contact, behaving in aggregate ways described beautifully by the statistical mechanics developed in the 19th century. Plasma is a collection of electrically charged particles, electrons and ions, that interact not just through collisions, but through the electromagnetic fields they collectively generate. Every charged particle in a plasma is simultaneously a source of electromagnetic influence and a responder to the influence of every other charged particle around it. In a dense plasma, where collisions happen frequently, the collective electromagnetic behavior averages out, and the plasma behaves somewhat like a fluid, describable by magnetohydrodynamics, the branch of physics that treats plasma as a conducting fluid threaded by magnetic fields. But in the corona, and especially in the solar wind, the plasma is sparse. Collisions are rare. Individual particles travel enormous distances between interactions. And in this collisionless regime, the plasma develops behaviors that have no analog in ordinary fluid dynamics. Waves that carry energy without transporting mass across macroscopic distances. Instabilities that grow from microscopic fluctuations to macroscopic structures through purely electromagnetic interactions. Particle populations that develop non-equilibrium velocity distributions. Populations where some particles move far faster than the thermal average, accelerated by resonant interactions with waves in the plasma that add energy to them each time they pass through the wave's phase front. The way a child on a swing gains energy if you push at exactly the right moment in exactly the right phase. This wave-particle resonance is one of the candidate mechanisms for the anomalous heating of the corona. Alfvén waves, named for the Swedish physicist Hannes Alfvén, who first predicted them theoretically, are transverse oscillations of the magnetic field that propagate along field lines the way vibrations propagate along a plucked string. They carry energy from their source and deposit it wherever they are damped. If Alfvén waves generated at the solar surface propagate upward into the corona and damp their energy into the plasma there through resonant wave-particle interactions, the corona would heat. Parker measured Alfvén waves inside the corona in unprecedented detail. It measured their amplitudes, the degree of magnetic field deflection as each wave passed the spacecraft. It measured their frequencies, their propagation directions, their relationship to the switchbacks and the plasma jets and the other structures in the corona, and it found that the alpha wave energy flux inside the corona is large enough, marginally, tantalizingly, to account for coronal heating if the waves damp efficiently. The word efficiently is doing enormous work in that sentence. Waves damp efficiently if there is a mechanism to transfer their energy to the plasma particles. In a collisional plasma, damping is straightforward. Waves lose energy to collisions, heating the plasma. In a collisionless plasma like the corona, damping requires a resonant mechanism. The wave must find particles traveling at the right speed to interact with it. And in the corona, where the particle velocity distribution is already anomalous, where there are already more fast particles than a simple thermal distribution would predict, the conditions for resonant damping may be met more readily than in a cooler, denser plasma. Parker's measurements of particle velocity distributions inside the corona confirmed the anomaly. The electron distribution functions, the statistical description of how fast the electrons are moving in every direction,